Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Delhi University. Today we are going to discuss about the module Fundamental Nature of Nuclear Materials from paper Energy Related Materials. So students, let us see what are we going to learn from this module. From these modules, students may get to know about the following. First, the difference between amorphous and crystalline nature of nuclear materials. Secondly, physical significance of space lattice and unit cell. Third, the crystalline systems and Bravais lattice. Fourth, polymorphism, which defines how the crystal structure changes with temperature. Lastly, the difference between a single crystalline and a polycrystalline material. So let us start with some introduction about the module. As we know that different applications required different properties of the material. The different properties of the materials facilitated different performances, which entirely depend on the internal structure of the materials. Hence, the understanding of the structure of the material is very important to know the inside information and achieved through various kinds of characterization. In this chapter, we will study and explore different kinds of material structures and their techniques for characterization. Now let us start with crystal structure. The solid materials are categorized on the basis of the uniformity with which the atoms of the ions are organized with respect to one another. On the basis of the arrangement of atoms, materials are classified in two categories, that is, crystalline and amorphous. A crystalline material is the one in which atoms are arranged in periodic manner in space over large atomic distances. All metals, various ceramics, and few polymers shows crystalline structure. The non-crystalline or amorphous material is the one in which atoms arrangement has no periodicity or long-range atomic order is absent. Most of the polymers and various ceramics are amorphous or non-crystalline in nature. Various properties of crystalline materials depend on their crystal structure, that is, the way in which atoms, ions, or molecules are arranged. A space lattice or crystal lattice can be described as an infinite three-dimensional array of points coinciding with the position of atom as showed in figure A. In ideal crystal, each lattice point has identical surrounding. Nevertheless, a set of lattice points about any given point are identical with the set of lattice points about other lattice point in the same crystal lattice. The long-range atomic order in crystalline solids is formed by repetition of small groups of atoms in space lattice. Hence, in order to describe a crystal structure, it is more suitable to subdivide the structure in small repeat entities. These small repeat entities are called as unit cell. A unit cell contains all information and element of symmetry of the crystal. The geometry of unit cell can be described by three lattice vectors, that is A vector, B vector and C vector, or by the axial lengths A, B and C and interaxial angles alpha, beta and gamma as shown in figure B. These three lattice vectors A, B and C and three lattice angles alpha, beta and gamma are called as lattice constants of the unit cell. The crystalline systems, different types of unit cells can be constructed by assigning specific values of lattice parameters, that is, by deciding the value of three edge lengths A, B and C and the three interaxial angles alpha, beta and gamma. However, crystallographers have found out that there are 7 different possible combinations of these lattice parameters, each of which represent a distinct crystal system. These 7 crystal systems are listed in the table below. Brevis lattice. There are 4 basic types of unit cells, which are number 1, simple, number 2, body-centered, third, face-centered, and last is base-centered. The combination of 7 crystal systems and these 4 basic unit cells results in 14 fundamental lattices, which are called as Brevis lattices. These Brevis lattices are shown in the figure. For cubic system, there are 3 types of unit cells, that is simple cubic, face-centered cubic and body-centered cubic. Tetragonal system has only 2 types of unit cells, simple tetragonal and body-centered tetragonal. In orthorhombic system, all 4 types of unit cells are represented. Hexagonal and triclinic crystal systems have only one simple type of unit cell. Monoclinic crystal system has simple and base-centered unit cell. Body-centered cubic crystal or BCC structure. The unit cell for BCC crystal structure has been shown in the figure below, where a central atom is surrounded by 8 nearest neighbor, that is 8 corner atoms, as evident from figure A, and is said to have a coordination number of 8. If we consider a single hard sphere unit cell structure from figure B, each of such cells occupies the equivalent of 2 atoms per unit cell, and 8 of a sphere located at each corner of the unit cell, making the equivalent of 1 atom, that is 1 by 8 multiplied by 8 equal to 1, plus 1 complete atom located at the center of the unit cell, results in total number of 2 atoms per unit cell. In BCC, unit cell center and corner atoms contact each other across the diagonal of the cube from figure C. Hence, in BCC unit cell, the length of the cube A and atomic radius R are related through the following equation. That is, a cubic diagonal is equal to root of the square of root 2a plus the square of a, which is equal to root or square root of 3a square and is nothing but equal to root 3 multiplied by a. Cubic diagonal is also equal to 4r, leading to the relation between the two as a is equal to 4r by root 3. If we consider that each atom in the BCC unit cell are spherical in nature, then the atomic packing factor APF for BCC crystal structure can be found out using the following relationship. APF is equal to volume of atoms in the unit cell, that is V atoms, divided by volume of the whole unit cell, that is V unit cell. V atoms is equal to the total number of atoms in the unit cell multiplied by volume of atoms, which is nothing but equal to 2 multiplied by 4 by 3 pi r cube is equal to 8.373 r cube, and V unit cell is equal to a cube. Hence, APF is equal to V atoms by V unit cell is equal to 8.373 r cube divided by a cube, which is equal to 8.373 r cube, and after putting the value of a, that is 4r by root 3 the whole cube, it is equal to 0.68. Hence, the APF for BCC crystal structure is 68%, which means 68% of the volume of the unit cell is occupied by atoms and remaining is empty. Since atom could be filled close together, hence BCC structure is not a closed packed structure. Various metals such as iron, tungsten, chromium, molybdenum exhibits BCC crystal structure. The face-centered cubic crystal or FCC structure. The unit cell for FCC crystal structure has been shown in the figure below, where atoms are located at each of the corners of the unit cell and at the centers of the faces of the unit cell, as evident from figure A. As shown in figure C, a FCC crystal structure has equivalent of 4 atoms per unit cell, that is an 8 of a sphere located at each corner of the unit cell, making the equivalent of 1 atom, 1 by 8 multiplied by 8 equal to 1, plus 6 half atoms on the faces of the cube contributed another 3 atom, that is 1 by 2 multiplied by 6 equal to 3, results in a total number of 4 atoms per unit cell. In FCC unit cell, face-centered and corner atoms contact each other across the cubic face diagonal, as evident from figure C. Hence, in FCC unit cell, the length of the cube A and atomic radius R are related through the following equations. That is, A is equal to 4r by root 2. The atomic packing factor for FCC can be calculated as follows. APF is equal to V atoms by V unit cell equal to 4 multiplied by 4 by 3 pi r cube divided by A cube is equal to 8.373 r cube, and after putting the value of A, which is equal to 4r by root 2 the whole cube, APF is equal to 0.74. Hence, FCC crystal structure has an APF of 0.74, which means 74% of the volume of the unit cell is filled with the atoms. Further, the APF of FCC crystal structure is greater than the APF of BCC crystal structure. The APF of 0.74 is the maximum possible packing of atoms of same diameter in a unit cell. Various metals such as copper, lead, aluminium, nickel, etc. have FCC crystal structure. The hexagonal close packed crystal or HCP structure. The HCP structure is the third most common metallic crystal structure as shown in the figure below. During solidification, most of the metals crystallize into HCP structure rather than simple hexagonal structure, because simple hexagonal structure has too low APF than HCP structure. The atoms in metallic crystals can achieve lower energy and more stable state by forming the HCP structure. Figures A and B shows the reduced sphere and hard sphere unit cell for the HCP crystal structure respectively. The HCP unit cell contains 6 atoms per unit cell, that is 6 multiplied by 1 by 6 atom sections on both top and bottom faces, making an equivalent of 2 atoms. 1 by 6 multiplied by 12 equal to 2. 3 interior atoms between the top and bottom faces forming a triangle, and 1/2 of an atom on the center of both top and bottom faces, providing an equivalent of 1 more electron. Thus, total number of electron in a HCP crystal structure unit cell is 6. Furthermore, the HCP structure has same coordination number and APF as of FCC, that is 12 and 0.74 respectively. There are various metals which belong to HCP crystal category are magnesium, titanium, zinc, cadmium, etc. So let's discuss about a polymorphism. A material which shows more than one crystal structure is known as polymorphism. It is also known as allotropy when it is found in elemental solids. Polymorphism basically depends on both external pressure and temperature. For example, pure iron has a BCC structure, which at higher temperature, that is around 912 degrees Celsius, which is 1674 degree Fahrenheit, changes to FCC iron. Variation in the density and other physical properties at higher temperature and external pressure results in polymorphic transformation. uranium, plutonium, and thorium show polymorphism characteristics. Point coordinates. Point coordinates are used to specify the position of any point located within the unit cell, and they are represented in terms of unit cell edge lengths, that is A, B, and C. Let us consider a point M within the unit cell shown in the figure below. Let us choose a set of generalized coordinates P, Q, and R to specify the location of point M. Here, P, Q, and R have some fractional lengths of A, B, and C along x, y, and z axes respectively. Hence, the location of point M is designated using point coordinates P, Q, R with values that are less than or equal to unity. For example, the central atom in BCC crystal lattice has position coordinate half, 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 and atoms on the cube faces in FCC have half, half, 0, half, 0, half, and 0, half, half. Crystallographic direction. A line between 2 points or a vector is defined as crystallographic direction. The study of crystallographic direction is important for the materials. Those properties are varied with crystallographic orientation. The crystallographic directions can be determined or diagrammatically be indicating in a unit cell using following steps. First, draw a direction vector of convenient length from an origin of the coordinate system or say corner of the unit cell. After that, determine the length of the projection vector along x, y, and z axis, which are most often measured in terms of unit cell dimensions A, B, and C. Further, divide or multiply these numbers by a common factor to get the smallest integers, which are called as direction indices. Finally, these direction indices are enclosed in square brackets without using separated commas. Figure below represents some crystallographic direction in a cubic unit cell. As shown in figure A, the position coordinates for the direction vectors OP, OQ, and OR are 100, 110, and 111. Hence, as per above discussion, the direction indices for OP, OQ, and OR will be square bracket 100, square bracket 110, and square bracket 111, which are the most common crystallographic direction in cubic unit cell. In figure B, the position coordinates of a direction vector OS are half, 1, 0. In order to obtain the direction indices, these position coordinates must be multiplied by 2. Hence, the direction indices of OS will be square bracket 1, 2, 0. In third situation, where the origin of the unit cell is changed as shown in figure C, the position coordinates of direction vector O prime U are -1, -1, 0. The negative indices are represented by a bar over the index. Hence, Direction indices of O prime U can be written as square bracket bar 1 bar 1 0 square bracket close. Generally, the letters U, V, W are used to represent the direction indices in the X, Y, and Z directions respectively, and written as square bracket UVZ. In a cubic unit cell, all parallel direction vectors have similar crystallographic direction indices. For example, in a cubic unit cell, all the cubic edge directions represented by the following indices are crystallographic equivalent directions. For convenience, the equivalent directions are assembled together into a family of directions and are represented by the angle brackets. The notation angle brackets 100 is used to represent cubic edge direction collectively or a family of cubic edge directions. Similarly, angle brackets 110 and angle brackets 111 presents the family of directions along body diagonal and face diagonal of unit cell. Crystallographic planes. Sometimes it is quite essential to mention a specific lattice plane of atoms within the crystallographic unit cell or to identify the crystallographic orientation of atomic plane or group of planes in crystal lattice. The crystallographic planes in a crystal structure are indicated by Miller indices, that is HKL. For a crystal lattice, the Miller indices are defined as the reciprocals of fractional intercepts that the plane makes with the crystallographic X, Y, and Z axis. The Miller indices HKL for cubic crystal lattice can be determined through the following procedure. First, select a crystallographic plane which does not pass through the origin at 0, 0, 0. However, if a plane passes through the origin, then either construct another parallel plane within the unit or establish new origin at the corner of another unit cell. Second, the crystallographic plane either intersects or remains parallel each of the crystallographic X, Y, and Z axis. The length of the intercept along X, Y, and Z axis is calculated in terms of unit cell parameters A, B, and C. Next, now take the reciprocal of these intercepts. A crystallographic plane which is parallel to an axis has infinite intercept and therefore gives a zero index. Lastly, multiply or divide these numbers by a common factor to get the smallest set of integers. These numbers are called as Miller indices of the crystallographic plane and are enclosed within parentheses without the use of commas. Generally, the notation HKL is adopted to specify the Miller indices, where H, K, and L are the Miller indices of crystal plane in a cubic unit structure has been shown in the figure below. In figure A, the intercepts made by crystal plane are 1, infinity, infinity along X, Y, and Z axis respectively. Now, the reciprocal of these intercepts gives 1, 0, 0. Hence, The Miller indices for this plane are 1, 0, 0. The crystal planes placed at equivalent position in the same unit cell are indicated by the same Miller indices. The set of equivalent lattice planes are called as the family of crystallographic planes and represented by the braces such as curly bracket HKL. Some equivalent crystal planes are presented in the figure on right hand side. Now let's discuss about the single crystalline and polycrystalline materials. In crystalline materials, where there is periodic arrangement of atoms which is perfect and can be extended through the specimen without any interruption, such crystalline materials are known as single crystal materials. Single crystals exist in nature and they can also be produced artificially. However, they are generally difficult to grow. In past few years, single crystal received from attention in various applications such as microelectronic, which nothing but utilizes single crystal silicon in electronic applications. Despite single crystal, most of the materials are composed of various small crystals or grains, and these kind of materials are called as polycrystalline materials. These grains, they have random crystallographic orientations and exist some atomic mismatch within the structure where two grains meet. This area is called as a grain boundary. So students, let us summarize what we have learned in this module. In this lecture, we have discussed several crystallographic structures, crystallographic plane, and crystallographic directions. These are very important to deal with the structural properties of nuclear materials. Next, various nuclear materials shows polymorphism nature, where structure of nuclear materials changes with temperature. Differences in single crystalline and polycrystalline materials have also been discussed. Thank you.